Similar to the way that I described earlier, that force problems are essentially just one type of problem, just dressed up with a silly hat. In a certain sense, another class of problems is going to be these projectile motion problems, which are all essentially the same problem, um, just dressed up slightly differently. So, kind of the most general projectile motion problem is that you have a scenario where you have some initial velocity of an object that's launched. The most general form is going to be it's launched from a different height than where it lands. The height is going to be x0, and it's going to have some point at which it peaks. So your book goes into pretty good detail and describes how to solve these problems. So in this video, I just want to describe a few tips and things to keep in mind, kind of common mistakes that I see people make. So one thing to note is that if x0 was 0 and this was launched from the ground, then this whole distance here, if we call this x, right, this is the range of the problem, then the peak is at x over 2, right? It's because this is a perfectly symmetric problem. Some other things to remember for problems like this. At the peak, the y velocity is going to be 0, right? You can imagine this is like, anytime you throw a ball up in the air, right? Its y velocity is getting smaller and smaller and smaller until it gets to 0, and then it becomes negative and it falls back down. So right at the peak, the velocity is 0. So one of the common ways to find out where the peak of this trajectory is just to find out the place where y equals 0. So essentially, these types of problems are going to be split into two halves. We have problem 1, which is going to be the time it takes to get to the peak. And we have problem 2, which is going to be the time it takes to get back to the ground or wherever it lands. Right? And so that also means that this whole first part is taking place in some time 1, second part's taking place in time 2, so that the total time is t1 plus t2. And so a lot of the time you'll actually solve these as two separate problems. Some other important things to remember are x component of acceleration is 0, right? Unless there was some sort of rocket or something else, in which case it's not really a projectile problem. So for projectile problems, the x acceleration is always 0, and the y acceleration is minus g. And one quick thing to note, anytime you're working on a quiz or an exam, and it should say these on there, but for the most part, you can always use g is going to be 10 meters per second squared, right? So we're just kind of rounding the 9.8 meters per second squared that you need to use on your homework for the book. But if we only have one significant digit, then this becomes 10 meters per second squared, and for quizzes and homework problems, it's just a lot easier to work with. So that's about it for these problems. You'll have, your regular equations of motion, just like you dealt with last week. So x is x0 plus v0t plus 1/2 a t squared. V is v0 plus at, right? Those are your equations of motion. You'd have one for x, and then you could also have one for y if x and y are different. In fact, this should actually be y0, not x0, because it's a height in the y direction. You might have multiple particles, right? Sometimes you'll have, you probably remember the question from a week or two ago when we had two balls that were dropping and you had to find out when they reached the same point. And that's just two equations of motion, but it's nothing different, right? Everything you do that's projectile motion is essentially two motion equations, and potentially broken up into two different problems, one while it's going up and one while it's going down. And kind of using this baseline and these facts, you can solve pretty much any problems that you end up getting. The other thing I will note is, in this case, v0 is a vector, right? And so if I give you this angle theta, then this here actually becomes V0 cosine theta, and here this is V0 cosine theta. And of course in x, there is no acceleration, right? In y, the acceleration would be minus 1/2 g t squared, and it would be minus gt. And of course, this would be sine theta on the v0, and that's if this was y. And that's basically everything you need to know to be able to solve a projectile motion problem. And again, these are going to get dressed up in different ways so that it might not look like it's this sort of problem. It might be kind of a seemingly different configuration, but they basically all simplify to, they're basically all more simple versions of this general problem.